In this video, I want to convince you that the properties that we mentioned in the preceding one are actually true. To keep the writing under control, I'm going to call the components of U A, B, and C instead of U1, U2, and U3. And likewise, I'll call the components of V by individual letters D, E, and F. The first thing I want to look at is the cross product of these two vectors in different orders. I'm leaving the word determinant out to make the writing more compact. If we expand U cross V in the usual way, the components of the answer are BF minus EC, the negative of AF minus DC, that is DC minus AF, and AE minus BD. This is U cross V. Calculating V cross U is very similar, except the first vector is V now, which has components D, E, and F, and the second vector is U, which has components A, B, and C. Doing the same sort of algebra, we find out that V cross U is equal to EC minus BF, AF minus DC, DB minus AE. If you look at U cross V, you'll see a connection. BF minus EC is the negative of EC minus BF. AF minus DC is the negative of DC minus AF. And AE minus BD is the negative of DB minus AE. This vector is the negative of that vector. By doing this, we've shown that if I take any two vectors U and V and form the cross product U cross V, it will be the negative of the vector that I would get by doing V cross U. The cross product of vectors doesn't obey a multiplicative commutative law. That's going to make things a little bit tricky, but we have verified it. This fact is always going to be true. This has an immediate consequence. If I take a vector U and form the cross product with itself, a certain result is always going to be the outcome. If I think of forming U cross U, I can mentally think of that one as being the first of the two U's and that one as being the second one. If I interchange those, the resulting cross product has had its sign reversed, but on the other hand, when I write this second U there and the first U there, it's still U cross U. Add the vector U cross U to both sides. U cross U plus itself is 2 times U cross U. U cross U plus the negative of U cross U is the zero vector. If I take a vector and cross product it with itself, I always get the zero vector. U cross U is identically equal to the zero vector. This goes on our list of facts that we have verified. If I have two vectors that are parallel, then their cross product is the zero vector. Remember that parallel means that one vector is a number multiplied by the other vector. As before, I'll let vector U have components A, B, and C, and I'll think about some number alpha multiplied by U. We multiply numbers by vectors by multiplying each component by the number. So alpha U is A times alpha, B times alpha, C times alpha. I want to look at U cross product alpha U and see if it comes up zero as I think it should. Writing out the determinant for U cross vector alpha times U, we end up with alpha times B times C minus alpha times B times C, which is zero. The negative of alpha times A times C minus alpha times A times C, which is zero. A times alpha times B is alpha times AB minus alpha times A times B. All three of those numbers are 0. If I take a cross product of two vectors that point along the same linear direction, the same straight line direction, the cross product of them will be the 0 vector. In ordinary algebra, if you take a number a and multiply it by the sum of b with c, what you get is a times b plus a times c. We know how to add vectors together, so naturally it's a question that you think of. Is there going to be a distributive law like the one that we've had before? Is u cross product the vector v plus w going to be the same thing as the two vectors u cross v and u cross w added together? The answer to that question turns out to be yes, and we can verify it in the same sort of way that we've done these other ones. In an effort to make the writing a little bit more clear, I'm using capital letters now. Next, I need to look at u cross v and u cross w separately. This is very direct. We calculate the cross products by doing the usual expansion. U cross v by itself turns out to have components bf minus ec, cd minus af, and ae minus bd, while u cross w has components bi minus ch, gc minus ai, and ah minus gb. If I add corresponding components of the two vectors together, I get the following horrific-looking expression. But if we compare this to the previous horrible and awful result, then we'll remember that u cross the vector v plus w was this mess. Look at the first components, and remember that capital A, B, C, D, E, F, and G, and H are just ordinary numbers, so those do commute under multiplication. B times F, B times F, plus B times I, plus B times I, minus the product of the numbers C and E, minus the product of the numbers C and E, minus CH, minus CH. The first components of those two vectors are always the same, no matter what these components are. And if you compare the second components, you see that they are the same also, and so are the third components. Another true statement is if I have a number times the cross product of two vectors, I can put the number on either one of the two vectors separately, just as you can do in ordinary algebra. I'll show that these first two vectors are the same. If you're feeling ambitious, you can then show that the third one is the same as the first two. Itself, what would be left is c multiplied by the vector with components beta mu minus gamma epsilon. In the second component, having pulled the c out, I'll have gamma delta minus alpha mu, and here I'll have alpha epsilon minus beta delta. This vector is the same as c times that vector. It's the same as c multiplied by the cross product of u and v. So we can now put this fact on our list of things we know for sure. We have an interpretation for the dot product in terms of the lengths of the vectors involved and the angle between them. I'd like some sort of similar thought concerning the cross product. The thing that's between us and getting the conclusion that we want is a sort of Pythagorean theorem. So we're going to have to establish this first. This is not difficult, it's just sort of tedious. I'd like to convince myself that the following fact is true. If I find the squares of the lengths of two vectors and multiply them together, that's going to be the same thing that I would get as if I took the dot product of the two vectors to obtain a number and then squared that, find the cross product of the two vectors, which is a vector, find the square of the length of it, and then add those two squares together. This is sort of a Pythagorean theorem. In order to establish this, it's perfectly straightforward, except it's just a big pile of algebra. So I'm going to select letters to represent the components of u and v. I'm going to calculate this quantity. I'll calculate this quantity and then say, looking at the two results, these things are always equal to each other. Not to make more out of this than it needs to be, I could think of this as a squared times this quantity plus b squared times this quantity plus c squared times this quantity. I can summarize the result by just saying I select two of these numbers, a, b, c, d, e, or f. I square the two numbers, I multiply them together, and I add up all things that look like that. So this is going to be magnitude of u squared multiplied by magnitude of v squared. This is the left-hand side of my equation. We calculate u cross v in the usual way and express it in component form. U dot v is a number. We multiply corresponding components of u and v together and add them up. The length of the cross product is going to be the easier of the two things to calculate. For this piece, that piece, and that piece, I'll just use the usual square of a difference formula. For the third piece, I'll group the first two terms together and use the usual distance. For the third term, I'll group the first two chunks together and then use the usual square of a sum formula, but I'll have to do it again to deal with the square of this piece. To further simplify this, I'll have to square the sum of AD with BE. Also, I'll use the distributive law to simplify this middle term. This is absolutely dreadful looking. Component from one of the vectors times the square of another component. But if you'll remember, when we calculated the square of the length of u times the square of the length of v, that's what we got. 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, each one of which looks like the square of a component times the square of some other component. This tells me that this number and that number are always the same. So this is a true identity here. This video is getting a little bit longer than I'd like, so I'm going to stop at that one, and I'll make a fourth video having to do with cross products only. In this last one, we'll find a geometrical interpretation for certain aspects of the cross product, and then use that to show how to calculate the areas of parallelograms and parallelepipeds. In the meantime, I hope everybody has a good day. I'll talk to you again soon.